Okay, so heretofore we've talked about the colligative properties in a qualitative way. Today you need to be able to talk about them in a quantitative way. So just because you've slept since the last time we talked about this, let us define this, that molality is equal to the moles of solute over the kilograms of solvent. And then one more useful thing for you to remember, and this formula is not written anywhere, people expect you to know that the molar mass of any compound is equal to the grams given over the moles present. Okay. So, remember you told me that the boiling point is always elevated when you add a non-volatile solute to a solvent. And the way you can quantitate this is the temperature change, the difference in boiling point temperature, the boiling point of the solution, is equal to Kb. Kb is the molal boiling point elevation constant of the solvent. Each solvent has its own value. Kb is a function of the solvent. I is the Van't Hoff factor of the solute. I belongs to the solute. The problem this morning was people had a very difficult time figuring out the value for I. You worry, I is greater than 1 only if there's ionization that occurs upon solution, so that's with an ionic compound. If it's a molecular compound, I is equal to 1. M stands for the concentration in molality of the solute. Delta T is the change in temperature. So you should be writing this equation down. The boiling point of a solution is equal to the boiling point of the pure solvent plus the change in temperature that's due to adding the non-volatile solute to the pure solvent.
Wait, what does that say?
The boiling point of the solution is equal to the boiling point of the pure solvent plus the temperature change due to adding a non-volatile solute to the solvent. Now, freezing is the temperature at which the vapor pressure of the solid and the vapor pressure of the liquid are equal. If you lower the vapor pressure of the liquid due to the addition of a non-volatile solute, then the vapor pressure of the solid has to be lowered as well, and therefore the freezing point is depressed. All right. Blah, 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 blah. Moving along. The change in temperature of the freezing point is equal to K sub F, which is the molal freezing point depression constant of the solvent. Once again, each solvent has its own value. I, the Van't Hoff factor of the solute, and M, concentration and molality of the solute. So the freezing point of the solution is equal to the freezing point of the pure solvent minus the change due to adding a non-volatile solute to the solvent.
The change in T is just the T that we put on the top? Right?
Yep.
Okay.
Okay. Now, it's really useful. Oh, I didn't change this part. Change this right here. It's really useful to be able to determine the molar mass of a solute using the freezing point depression or the boiling point elevation. And in order to do this, these are the steps that you would take. Number one, using your equation that the change in temperature is equal to the molal boiling point times molality times I, solve for molality, the molality of the solute. Once you have the molality of the solute, you figure out the moles of the solute by utilizing the molality times the kilograms of solvent. So then you have the moles of the solute. You can determine the molar mass of the solute by figuring out how much solute they put into the solution. This will clear in a sec. And divide it by the moles of solute. All right. This is you doing one of these problems. Is there a pause button on that? I don't think there is.
I can stop recording and record
Yeah,
again.
then go ahead and stop recording. I'll just make another file.